All right, so we're going to go over this exam practice now. So the first thing that we're going to want to do is we're going to want to rewrite this fifth root as 1/5 power. So it's going to be x5 minus 3 all to the 1/5 power, and then over x plus 7. And then we're talking about the limit as x approaches infinity. So you could say that this 1/5, or as the limit approaches infinity, these constant terms don't really matter. So then this is the same thing as the limit as x approaches infinity of x5 to the 1/5 divided by x. And so then now you can say, okay, well, this 5 cancels with this 1/5, and then this whole thing is equal to the limit as x approaches infinity of x over x, and that is the same thing as the limit as x approaches infinity of that x cancels with this x, and you get 1. So your answer is 1. Okay, so now for the next problem B. So this one is, so the first thing we always do is we want to try direct substitution, right? So the e to the 1 over infinity, anything divided by infinity is 0, right? So that's e to the 0 over infinity plus infinity. So we can simplify that a little bit. E to the 0 is 1. Anything to the 0 power is 1, right? So that's 1 divided by infinity plus infinity. Anything divided by infinity is 0. So that's 0 plus infinity, which is just infinity. So there's no L'Hopital's rule necessary for this problem. You kind of think of it as like a trick problem. I could definitely see something like that being on the final, something where you need to just do direct substitution and it'll work. Just so make sure to always try direct substitution because it can sometimes work. Okay, so but for C, it's probably not going to work, right? So when we plug in infinity there, we get 4 times infinity to the 1 divided by infinity, and that's going to be infinity to the anything divided by infinity is 0, so it's going to be infinity to the 0, which is an indeterminate form. And so then we're going to do that ln thing. So we're going to say ln y equals ln limit as x approaches infinity of 4x to the 1 divided by x. And then due to the properties of limits, that ln can move inside of that limit. And we get this. So now, due to the properties of logarithms, that ln can come down. So ln y equals limit as x approaches infinity of 1 divided by x times ln of 4x. So then, in order to use L'Hopital's rule, right, we want to rewrite this as a fraction, because in order to use L'Hopital's rule, you need a numerator and a denominator. So limit as x approaches infinity of ln of 4x, and then the fraction is very obvious, right, that x just is in the denominator. Okay, so now we can say ln y equals limit as x approaches infinity, and this is where we're going to use L'Hopital rule, because now we have a numerator and a denominator, so we can actually use it. So the derivative of the numerator, the derivative of 4x, is going to be 1 divided by 4x times 4, and then the derivative of our denominator is going to be just 1. And if this derivative seems a little bit weird to you, make sure to review chain rules and the derivatives of logarithms. So this is, that simplifies to 1 over x, and then that 1 just kind of gets lost or whatever. So then we would have ln y equals the limit as x approaches infinity of 1 over x, and so that's ln y equals 1 divided by infinity. Anything divided by infinity is 0, so we get ln y equals 0. So then we have to take the e of both sides. So we get y equals e to the 0 is just 1, because anything to the 0th power is just 1. So our final answer for this is going to be 1. All right, so the next problem we're going to talk about is the related rates problem. Now there's like 800 different related rates problems there could be. This is just one of them, so I suggest that you study by doing a lot of different related rates problems. This one is statistically not likely to be the one you'll see on the final, but this is a type of approach, and this is going to be one of the trig related rates problems. So the picture for this is honestly the hardest part. But it's going to look like this. So this is our theta, then the sun is up here, and the building is here. And so we said the building is 400 feet tall, and the d theta dt is going to be 0.25 radians per hour. And at the specific moment, the theta is pi over 6. So what we do now is we're looking for a trig function from SOHCAHTOA that's going to give us useful stuff. And so this, which I will call a shadow, right, because this is the shadow being cast by the building, we're actually looking for ds dt. We're looking for the rate at which the shadow cast by the building is increasing. So that means our trig function that we choose, we're going to want to incorporate this side because we already have information about that side. And we could also say that if we call this b, because building, db dt equals 0, right? The building itself is not changing in height. So we want our trig function to incorporate the building because we know stuff about the building, and the shadow because we want to find out stuff about the shadow. So for that reason, we're going to pick tangent, right? Because we have opposite, which is the building, and adjacent, which is the shadow. So when we do that, we get tan theta equals opposite, building, which would be 400, over adjacent, which is the shadow, S. But actually, before we do that, let's just do B over S, right? Building over shadow. And then now we're going to take the derivative of this. So we get secant squared theta times d theta dt equals, and this is going to be a quotient rule where u equals b, v equals s, quotient, or u prime equals db over dt, v prime equals ds over dt, and then that's u prime v minus uv prime over v squared. So then that's going to be db dt times s minus b times ds dt. And that's going to be all over s squared. So that's going to be our thing that we need to solve. And so we know dB dt is 0, right? So we can immediately say, okay, secant squared theta d. Oh, and we also know d theta dt, right? So that's going to be 0.25 equals, we know dB dt is 0, so we're just going to be left with negative b times ds dt divided by s squared. And we know in our moment that theta is going to be pi over 6. So we get secant squared of pi over 6 times 0.25 equals negative, we know the building is 400, building is not changing height, ds dt over s squared. And ds dt is what we're trying to solve for, right? So let's just simplify this in terms of ds dt. So we can multiply both sides by s squared, so we get s squared times secant squared of pi over 6 times 0.25, and then we could also divide by that negative 400 equals ds dt. But we're not finished yet because we can't actually get a number from this, right? Because we don't know what our value of s is. So that is when we make our moment triangle. So what that means is we're going to make another triangle. Our building is still 400, but in this case, we're looking at the triangle when pi over 6 is our theta. So if pi over 6 is our theta, tan of pi over 6 equals 400 over shadow, right? So tan of pi over 6, that would be 1 over square root 3 equals 400 over shadow. So we can multiply both sides by shadow and then multiply both sides by, we can basically just cross multiply, right? Shadow equals 400 times the square root of 3. So now we just have to, instead of s, we put 400 root 3. So then that, I'm trying to think if you'd be expected to simplify past this. Well, we could, so this would be 400 times 400 times 3, because that 3 just gets squared, times secant squared of pi over 6. Secant squared of pi over 6. Well, cosine of pi over 6 is root 3 over 2. Yeah. So if cosine of pi over 6 is root 3 over 2, secant is it root 3 over 2? I don't know. What is cosine of pi over 6? Okay, it is root 3 over 2. So then secant would be the inverse of that. So 2 over root 3. And that would get squared. Times 0.25 or 1/4 divided by negative 400. So you could say one of these 400s cancels with one of these 400s. You could take this 1/4 and make this 400 a 100. And then for this, right, you could make the top a 4. And that bottom just becomes a 3 instead of a root 3, you know what I mean? And then this 3 cancels with this 3. And then, oh yeah, we don't have this anymore. And then, so that's negative 400. ds dt equals negative 400 rad per hour. So then it's asking when we're decreasing, or sorry, asking where we're increasing. So then this would be our answer. All right, wait, I'm sorry. So one thing I missed, and be careful about this, is it says the angle of elevation of the sun is decreasing at a rate of 0.25 rad per hour. So there needs to be a negative sign here, and basically everywhere there needs to be a negative sign. But so the only place it really impacts stuff is here. So this would be a negative. So then this negative would cancel with this negative, and we would get a positive 400 rad per hour. All right, so the next thing we're going to talk about is the optimization problem, and this particular optimization problem is dealing with the cylinder. So it's dealing with the surface area and the volume of a cylinder. I can't really say whether you be expected to know these formulas on the exam. I'm really not sure. That'd be a question for the professor or the TA or something. But so let's walk through it. And just in case you're not familiar, the volume of a cylinder is pi r squared times the height, and the surface area is going to be equal to 2 pi r h plus 2 pi r squared. So knowing that, those are our two formulas. It'll hold a volume of 10 cubic feet, so we're looking for a V of 10, and we want to minimize the surface area. Okay, so that means that we're going to need to solve for volume and somehow plug it into the surface area. So it's going to be, since our v is 10, 10 equals pi r squared times height. And so now we're going to need to solve this in terms of r or in terms of h. It's going to be best to solve this in terms of h, just because if we solved it in terms of r, we have to plug it in here, and then square it, and that just gets all kind of messy. So we're going to solve it for h. And it's going to be easier to solve it for h too, right? H equals, we just divide both sides by pi r squared. So h is going to be 10 divided by pi r squared. So now we go and we plug that in to our surface area formula. And we get that the surface area equals 2 pi r times 10 over pi r squared plus 2 pi r squared. Okay, so then another thing we could do is this r squared could cancel with this r. And then, so then now we're dealing with SA equals, oh, and this pi cancels with this pi. So we're really dealing with, was that 20 over r plus 2 pi r squared. So now, in order to take the next step, we got to take the derivative of this. So SA prime equals, this is going to be negative 20 over r squared, and that's a power rule problem where you would first rewrite it as r to the negative 1, and then you do the power rule on it, and you would get negative 20 times r to the negative 2, and then you would just move that negative 2 down to the denominator. Over here, this is a more simple power rule for pi r. So now we got to make a sign chart of this stuff. So to make a sign chart, we set it equal to 0, right? So 0 equals negative 20 over r squared plus 4 pi r. So if we subtract, or if we add negative 20 over r squared to both sides, 20 over r squared equals 4 pi r. So now we can multiply both sides by r. So we get 20 equals 4 pi r cubed. And then we can divide both sides by 4 to get 5 equals pi r cubed. And then we could divide both sides by pi to get 5 over pi equals r cubed. And then we could take the cube root of both sides to get the cube root of 5 over pi equals r. So that's going to be our point on our sign chart. It's going to be the cube root of 5 divided by pi. That's going to be our r value. So to the left of this, we can see if we plug in something to the left of this, so this is a positive number, so if we plugged in like 0, right, what would we get if we plugged in 0? Actually, wait, we can't do that because this is illegal. So what about like 1? What if we plugged in 1 for r? So then we would end up with negative 20 plus 4 pi. Pi is 3.14, so that'd be like, what, a little over 12? And that would be still a negative, or not negative 20, but negative. So then this whole thing is negative. And if we plugged in something to the right, that would be positive. Yeah, because if we plug in something to the right, that's going to be positive. Okay, cool. So now, and that makes sense, right? Because if we're looking to minimize the surface area, then we want to find a local min, right? Because then it's like, oh, okay, we actually have a minimum. So since we only have one critical point, we actually don't need to argue that it's a minimum. But so let's plug it back into the original function just to figure out what our, actually no, we're going to save that for the end. So, but if you didn't, you need to use the second derivative test, and you only need to use the second derivative test if you have more than one critical point. And in this case, we only have one critical point, so we do not need to do this step. But on some problems, you do have to do the second derivative test, in which case you would just take the derivative of this, and then if it's positive, then you have if it's positive at here, then you have a local min there. Okay, but so since we don't need to do that, we are chilling. So the last thing that we're just going to do is we're going to plug this R value back into our volume formula to also solve for our height. So our volume is 10, right? And volume equals pi r squared h. We said our r is the cube root of 5 divided by pi. So it's going to get squared. And then we're going to multiply by h. And we're trying to solve for h here. So h is just going to be 10 divided by pi times 5 divided by pi to the 2/3 power. And I don't really care to solve that anymore. So our final answer is going to be, since it asks us for the dimensions, we need to give them the radius and the height. And so, yeah, so it's going to be these two things, the radius and the height. All right, so then the next section, you're probably going to see about 3 questions on just straight up finding the derivatives of stuff. And this isn't too bad. You just need to know your like inverse trig derivatives, your power rule, your quotient rule, your product rule, your chain rule, and the fundamental theorem of calculus part, is it 1 or 2? It's this one. Oh God, I can't remember if it's part 1 or 2. But anyways, so there's a lot of stuff to remember here, but a lot of it is familiar. Another thing you're going to see is a lot of stuff within a problem. So like you can see this one. This is going to be chain rule and product rule inside of a quotient rule. But if you're just methodical, you take your time, you don't rush it, you're going to be totally fine on this section. And it should be not that bad, maybe even some easy points. So just for this one, so the first thing we're going to do is we're going to rewrite it as 4 times x to the 5/7 power minus 3 tan inverse of x cubed. So this is going to be able to make this first term just like a nice and simple power rule. So then in a power rule, right, we multiply by the power, so 5/7 times 4x, and then we drop the power by 1. So 5/7 minus 1 is a negative 2/7. And then over here, that 3 is going to stay the same, and the derivative of tan inverse is 1 over 1 plus x squared. So that would be 1 over 1 plus x cubed squared, right? Because we have to still think about this inside. That gets plugged in for this x. And then this is also a chain rule, so we have to multiply by the derivative of x cubed, which is 3x squared. So now we can simplify this a little bit. We get 20, right, because we multiply that 5 and that 4. So 20/7 times, so we got x to the negative 2/7, which we can just move down to the denominator and make it a positive 2/7. So then we get minus, we could combine these two 3's to be a 9x squared divided by 1 plus x to the 3rd power to the 2nd power is going to be x to the 6th power. And, man, this might be it. Is there any way we can simplify this? No, I think this is pretty good. So, yeah, this should be a pretty good answer for this one. So just remember your inverse trig derivatives and how to rewrite your powers and stuff like that, and you'll be all right. All right, so then for B, this is going to be 3 rules that we've seen a lot this semester. It's going to be chain rule, product rule, and quotient rule. So the whole thing is a quotient rule, right? So, and just a reminder, the quotient rule is u prime v minus uv prime over v squared. So our u is going to be our numerator, x to the 6th power plus 9x, all to the 2nd power. Derivative of that is going to be a chain rule problem, which is going to be x6 plus 9x to the 1st power times the derivative of the inside, which is going to be 6x to the 5th plus 9. So, and we'll probably want to simplify that at least a little bit. So then our v is going to be x to the 4 times e tangent of x. And that is going to be a product rule, where our u is x to the 4, derivative of that is 4x cubed, and then our v is going to be e to the tan x. Derivative of that is going to be a chain rule, where our outside function is e to the x, and our inside function is tan x. The derivative of e to the x is e to the x, so the derivative of our inside function is e to the x. And then g prime of x, the derivative of our inside function, is going to be secant squared of x. And the chain rule formula is f prime of g of x times g prime of x. So that is going to be e to the tan x times secant squared x. So now the v prime for our product rule is going to be e tan x times secant squared x. And so then the v prime, and I'm going to move this down here, the v prime is going to be this times this, x4 e tan x secant squared x plus 4x3 times e tan x. So actually, I don't want to simplify this. So now for the quotient rule, now we're back to the quotient rule. We're going to go u prime, so that's going to be x6 plus 9x times 6x to the 5th plus 9. That's just our u prime. And then our v is x4 times e to the tan x. And then we're going to subtract from this our u, which is going to be x to the 6th plus 9x squared times our v prime, which is this whole stuff. Ah, shit. So x4 e tan x secant squared x plus 4x cubed e tan x. And then that's all divided by v squared, v being this, right? So that's x4 times e tan x. And that all gets squared. So this is going to be your monster of a final answer. All right, so C is going to be a fundamental theorem of calculus part 1 type of problem. So I've written out the FTC part 1 just in case you need the reminder. So basically all that means is we take this 3x squared and we plug it in everywhere we see a t. So that's going to be 3x squared times e to the sine of 3 times 3x squared. And then we also have to multiply, right? Because this part, the like chain rule part, if you will, we still have to multiply by the derivative of 3x squared, which is just 6x. And probably simplify this at least a little bit. You can go 18x cubed times e to the sine of, that could be 9x squared, right? And I'd say this is probably a good place to leave it. Next up, we got integrals. For this first one, you got to remember that one of the properties of integrals is that if you're subtracting inside the integral, you can also be subtracting outside of the integral. So you can actually split this up into 2 different intervals, and it's going to make this problem doable. So for this first one, we could say, so I always like to rewrite it as we rewrite this first one as 5 times x to the negative 1 dx minus 4 times x to the negative 3 dx. And another thing we can do is we can bring these constants out in front. So then we can think about, so we got 5. The antiderivative of x to the negative 1 is ln of x. And this gets evaluated from e down to 1. And then we subtract from that 4. The antiderivative of x to the negative 3 is, remember for reverse power rule, we add 1 to the power, so that's x to the negative 2, and then we divide by that power. So x to the negative 2 divided by 2. And we got that from 1 to e as well. So now we can say, all right, 5 times ln, so this is going to be ln of e minus ln of 1. And then minus 4 times, this is going to be negative 1/2 times, or sorry, let's put this x back in the denominator, you know what I mean? So this is going to be negative 1 over 2x squared. So then we can say, okay, so that's negative 1 over 2e squared minus negative 1 over 2 times 1 squared. So then we can simplify this even more, because it's like ln of e is just 1 minus ln of 1 is just 0. So we got that minus 4 times, so that's going to be negative 1 over 2e squared plus 1 over 2. And then we could simplify that as 5 minus, let's distribute that 4. So let's go 5 plus 4 over 2e squared. We could take that 2 out. This becomes a 2 up here. So plus 2 over e squared plus 1/2 times 4. Okay, that's going to be a minus because it's a minus 4. So that's going to be negative 2. So then our final answer would be 3 plus 2 over e squared. All right, so B is going to be a U-sub problem involving trig. And so this one's kind of difficult, but you know, all these U-sub problems are really just a puzzle. And you could try, you really have 3 different candidates for what your U could be. So if you just try all 3 of them, you'll find which one actually works in the right amount of time. The correct pick for your U here is going to be cotangent of theta squared. And that's because the du of that is going to be a chain rule problem, right? So the derivative of cotangent is negative cosecant squared. So that's going to be of theta squared. And then you also have to, since it's like a chain rule, you got to multiply by the derivative of the inside, which is 2 theta d theta dt. Or sorry, just d theta. What am I doing? I'm trying to undo. All right, so that's our du. So now we kind of got to make this puzzle piece fit a little bit. So we got a positive cosecant and cosecant squared of theta squared, and we've got a theta, right? But we don't got a 2, and we don't got a negative sign. So then what we're going to do is we're going to divide both sides by a negative 1, or sorry, we're going to divide both sides by a negative 2. So that's going to be negative 1/2 du equals cosecant squared of theta squared times theta d theta. And you're going to notice that that's exactly what we have here, right? Both these terms get taken out by that on this d theta too. So then you're going to be able to rewrite this as u, because right, we're saying our u is cotangent of theta squared. U du no, u times 1/2 du is our new integral, right? So now we can move that 1/2 out front, and we say negative 1/2 times u du, and now we're like just doing a power rule or a reverse power rule, you know what I'm saying? Because it's u to the 1. So when we do the reverse power rule, we add 1 to the power, and so we get negative 1/2, and then so we add 1 to that power, and then we divide by that power, so that's u squared divided by 2. And so then we can simplify this whole thing, and it's like negative u squared over 4, right? So then the last thing we got to do is we got to plug back in for our u. So what did we say our u was? cotangent of theta squared. So that's going to be our whole thing. And so then that all gets squared, or it gets negative and then squared. And then that's all divided by 4. So this would be, yeah, this would probably be your final answer. Oh, and one error. I think like one of these equal signs got copied over, so I don't know why there's a negative sign here. That's a regular cotangent. I don't know how that got there, but yes, this is going to be the answer. All right, so this is like, I've been staring at this problem, number C, for like 10 minutes, and I just realized there's a typo. This is supposed to be a negative, not a positive. And you guys are going to see how much this changes the actual problem. So our u is going to be 4x squared minus 6x. Derivative of that is going to be 8x minus 6 dx. And so now we're like, we have something that kind of looks like what we're looking for here, but not quite. So if we divide both sides by 2, we get 1/2 du equals 4x minus 3 dx. So that's something that we actually have in the problem. So we can rewrite this as the integral. The numerator is 1/2 du, and the denominator is the square root of u. So we can rewrite that as, we can bring that 1/2 out front. So 1/2, and then the integral of 1 divided by the square root of u, du. So then we can do 1/2, and then the times the integral of u to the negative 1/2 power, du. And then when we do that, we add 1 to the power. So we get 1/2, and then we divide by that power. Dividing by 1/2 is the same thing as multiplying by 2. And then this 1/2 cancels with this 2. So we're just left with square root of u. So the answer is the square root of, and then we plug back in for u, obviously. 4x squared minus 6x. And that is the answer that we're going to get for this problem. All right, so the last subject before we talk about the true or false section is going to be the precise definition of a limit, or the formal definition of a limit, whatever. So this one kind of slips through the cracks a lot, just because it's like, this was something we talked about at the beginning of the semester, but it'll probably find its way onto the exam. And so if you forget it, because I mean, it doesn't really build on anything, right? It's kind of something you just can kind of forget about after we study it. But so, and it does pop back up, and you know, it really sucks if you're not prepared for it. So this is the precise definition of limit, right? This, and I can't say whether or not you'd be asked for the formal proof or not. I'm not gonna write the formal proof, but just because it's a lot of words and it's not really worth the time. But revisit the lecture notes if you'd like practice writing the formal proof. I can't say whether or not you will or will not, just because I mean it's a common final, so you know every professor has input on this, so it's really just kind of a guessing game. So, but what we can talk about is the fact that a equals 1, right? A is what the x value is approaching. So if x minus a is less than delta, then f of x being this, 2x minus 4 minus L is this, negative 2, is less than epsilon. So we can simplify this part a little bit, right? So 2x, we got a minus 4 and a minus minus 2, so that would be negative, just straight up minus 2, right? Less than epsilon. We can simplify this a little more, right? We can factor out a absolute value of 2. So that's x minus 1 is less than epsilon. So, and the absolute value of 2 is just 2. So then we can divide both sides by 2. X minus 1 is less than epsilon over 2. And as you can see, this looks a lot like this. So that means that we're done, and we have successfully chosen our delta value. So we say we choose delta to be equal to epsilon over 2. All right, so the true, false, and or the multiple choice part of the exam is kind of where you see like a little bit of everything, and it's really impossible to predict exactly what the questions are going to be like on this part of the exam. But you're going to see your theorems in there. This is where you're going to find your theorems, things like the mean value theorem, intermediate value theorem, Rolle's theorem, definition of continuity, that sort of thing. Maybe even the limit definition of the derivative or something like that. Let's just get into it. So A, if f is differentiable at c with f prime of c equals 0, then f has a local maximum or a minimum at c. This is going to be false. This because it could be a straddle, right? Because a min has to go from decreasing to increasing on either side of the place where f prime of c equals 0, and then a max has to go from increasing to decreasing at the place where f prime of c equals 0. If it goes negative to negative or positive to positive, then these are straddles. So it is not sufficient to say that f prime of c just has to be equal to 0. You also have to switch your signage on either side of the interval. All right, so then for B, we're looking at the IVT here. So the IVT is asking about this picture and is asking if it applies for this point, C and N. So this one is going to be no, it does not apply here. So basically, I'm not going to write it all out, but your argument would basically be like, the IVT guarantees this. The IVT guarantees that this whole thing is going to be somewhere, you know what I mean? But if because the IVT states that between A and B, the function takes on every value between f of A and f of B. At C, N is not between f of A and f of B, right? N is less than A, so it's not on the interval, so it's not guaranteed by the IVT. So that's something like what your argument would sound like. So then C is going to be false, and this one's not too bad actually, because remember, in order to be differentiable, you must be continuous. So if this said if f is if f is differentiable at A, then f is continuous at A. So if these were swapped, then it would be true. But they're not swapped, so it's false. It's kind of like a rectangle and a square thing. Just because it's continuous doesn't mean it's differentiable, and your counterexample for this would be like a cusp or a corner, where you have a function that is continuous but not differentiable. And just kind of in closing, I just wanted to show the different other subjects, like shorter calculations that you'd probably see on something like the multiple choice section or whatever. We got Newton's method, random limits, random derivatives, integrals, antiderivatives, Riemann sums, partial sums, rewriting definite integrals as Riemann sums and vice versa. That one's kind of important because if you just kind of forget about it, then you're kind of screwed. So just review that formula, which was from about like a month ago at this point. And then, so you probably aren't going to see a curve sketching problem just because they take so dang long, and you only have so much time for the final and you got to fit all that other stuff in. But the content of curve sketching problems is still probably going to find its way onto the exam in one form or another, and that's probably going to be something like analyzing the first and the second derivative. So you're not going to be expected to do a whole curve sketching problem. God, I would hope not. But you might be asked for stuff about first derivative, second derivative, etc. And then finding equations of the tangent line. Basically, by that, it's just like, remember, y minus y1 equals mx minus x1. Remember your point slope form. And, right, your derivative is your m, right? The m is the slope of your tangent line, m is your derivative. Derivative is the slope of the tangent line, that sort of thing. So just remember your point slope form. I know it's going way back, and that your m, or your slope, is your derivative. So other than that, I'm trying to think, is there anything else? This is not exhaustive, obviously. Like, especially this true-false stuff. Like, don't just study A through C and being like, okay, I understand it, that makes sense, I should be all good on the multiple choice section. It's probably not going to be these questions on the exam, but just make sure you have an understanding of the different theorems and their implications and the definitions of things like continuity and stuff like that. So, thank you all for a great semester.